Okay, good morning everyone. First things first, your homework was supposed to be due this Friday, okay? Not this Friday, but Sunday, one of those days. And I've just made the due date to be March 22nd. So if you want, you can submit the homework towards this weekend. I'll still hold my office hours and so on, but if you plan to travel for spring break and you're not going to be around on the weekend, you can come back and then submit it after that. Okay, does that sound reasonable to everybody? Okay. So this I sent an email yesterday, I think. So homework will be due 11:59 p.m. I'll be posting it tonight. You should still be able to complete the homework by this weekend based upon lectures of the past week and this week. But if you chose to not do so, you're welcome to submit it on the 22nd. I've graded your midterm exams and they have been uploaded on Carter. Okay, if you have any issues in the grading, please contact me. Okay, so what I want to do is I want to start off with a problem today, and then we will start talking about an ideal surface and the Planck distribution and so on. So, this is once again regurgitation of material that we've seen in the past, but there are like multiple definitions, and I want everybody to be on the same page, okay, in terms of these definitions. So here's the problem. I have an ideal diffuse emitter. And the spectral intensity is given as the following. So notice spectral intensity, which means that this is only a function of the wavelength, it is not a function of the direction. So any quantity, if you say is a spectral quantity, is typically going to have either the directions integrated through or it's going to be independent of the directions. So that is given as a following. Did I scare him away? I lambda comma a says a triangular linear portion. 0, 10, 40. This is so many micrometers, wavelengths typically in micrometers. The spectral intensity typically has units of watts per meter square micrometer steradians. So this is watts meter square micrometer. SR is steradians, and this value here is 10 to the power 4. Okay, so this is the situation that we are shown. We are asked to obtain the following. So I'm going to list them one by one. First one. Obtain the spectral flux dq double prime lambda about some theta phi direction, okay, about a particular direction. Second thing, obtain the spectral emissive flux of the hemispherical spectral emissive flux E lambda. Okay, this is going to be a function of only lambda. And obviously temperature. Any radiation dependent phenomenon is a function of temperature, the thermal radiation, okay, for us. Then the third thing, obtain total emissive flux. Well, you know, right? I should have been in the NBA. Total capital E. So this emissive flux sometimes is also called as emissive power. Whereas, though you've got to be careful, doesn't mean that it's watts, the units are watts per meter square in this case. So it's also called as emissive power. So obtain all these quantities. That's for this first part of the problem. And then the second part of the problem, we are going to consider the following. A square plate with this radiation spectrum is sitting. This is area A1, 10 to the power 4 meters square, some square plate. This is emitting radiation that follows the spectral distribution as you have shown there. And it's emitting about a hemispherical shell. Okay. You have said that, you're told that, okay, here is a particular direction to consider. So here is this direction is the area normal to the plate. Okay. And at an angle of 60 degrees to the area normal of this plate. There is another plate that is placed, but this plate is not placed on the hemisphere, it's placed at an angle to the hemisphere, so it's placed vertically here. So you're just seeing the front view of this plate, which is going to be a straight line. Okay, so this is another plate whose area is the same, so this is A2. 10 to the power 4 meters square. The issue here is that the area normal to A2, if I draw it, n hat 2 is the area normal to A2, n hat 1 is the area normal for A1, which is that straight line there. So you see that the area normal n hat 2 is not along the line of sight from the position of an observer sitting in A1. Okay, the line of sight is this line here, all the way to that area there, but this area is not placed in the hemisphere, so the area normals are at an angle with respect to the line of sight. What are we supposed to do here? We are supposed to find out the flux, the total flux, Q12 double prime that is received by A2. And you're asked to consider this area A2 to be very small. Obviously, the number implies that. A2 is small area. And from last time, the distance from point A1 or the radius of this hemispherical shell that we're asked to consider is 50 centimeters. So this distance here is R12, which is 50 centimeters. Okay. The difference from what we did last time was that this area A2, the problem that I solved on Friday, that was sitting on the hemisphere. So that the area normal of that plate was along the line of sight from a person sitting in A1 and looking at A2. This is slightly different. Okay? Okay, let's get going one by one, and then we'll go into the ideal surface definition and the Planck distribution. I'm going to start from the definitions. So we define intensity in the following manner, or rewriting the formula from before. dq is I lambda comma E. Notice we are looking at the emission characteristics at this point in time. Lambda, theta, phi, d lambda, d omega, dan, I'm going to verbally define these terms, not write them out. The first term dq is the rate of radiant energy that is emitted by this plate A1 about a particular direction theta and phi, and for a particular fraction of the wavelength d lambda. That's the radiant rate of energy that is emitted. And you can see the fractions here. The presence of d omega implies, okay, what's the directionality that this emission is taking, the dependence on the direction. The presence of d lambda implies that, okay, this is a function of the wavelength. This creature is stuck here because depending on where you are sitting on the hemisphere and looking down on the emitting area, you are not going to see the total intensity to be the same everywhere. It's going to change depending on the projection of this area along the line of sight. So this typically we know as dA times cosine theta, right? So this is the net radiant rate of heat transfer. I'm going to do the following. dA cosine theta, I'm going to bring this dA and divide through there and I get the flux. So dq double prime is dq by dA. I'm interested in everything happening throughout the hemisphere, so I'm going to write the solid angle as sine theta d theta d phi. This is I lambda e lambda theta phi d lambda sine theta d phi cosine theta, because I took the dA and then I brought it here. What is this term? This is the emissive flux over a fraction of the wavelength range d lambda and for a specified direction. Now, I'm going to divide this emissive flux by the fraction d lambda, and here is what I'm going to end up getting. dq double prime lambda. This we are going to define as dq double prime by d lambda. This is the spectral emissive flux. About a specified direction. Does this make sense everywhere? And if I want the total spectral emissive flux, all I have to do is integrate over the angle d theta d phi. Go from 0 to 2 pi, go from 0 to pi by 2, and I get my first quantity here, which is, or the second quantity here, which is the hemispherical spectral emissive flux, or the total spectral hemispherical emissive flux. So E lambda is now the integral of d lambda or dq double prime lambda over all the wavelength. And so this is going to be, I'm sorry, over all the directions. So this is 0 to 2 pi. 0 to pi by 2, I lambda comma e and all these other creatures. Lambda theta phi sine theta cos theta d theta d phi. Okay, so this is the second one that we are defining here, the hemispherical spectral emissive flux. And we are in a position to calculate this for our particular problem because of the fact that the intensity is independent of the directions. So I of lambda comma theta comma phi is just IE of lambda and temperature only. So for us, so diffuse emitter, so IE lambda comma E is just a function only of the wavelength and obviously the temperature. Most times it is not necessary to write the temperature, it is implied. All these are dependent on temperature. Okay? And so E lambda for our problem is I lambda comma E integral 0 to 2 pi by 2 sine theta cos theta d theta d phi. This integral has been evaluated many times over the past couple of lectures. This answer is equal to pi steradians. And so E lambda for us. We have not been asked to calculate the numerical value. We've just been asked to obtain an expression for it. Okay? So for our problem, E lambda times pi. Look at the units. Pi is in steradians. I lambda comma E, as you can see from the plot there, is watts per meter square micrometer steradians. And this is essentially watts. So this is the unit for E lambda. Okay? This is, so let me label, this is part 1 of the problem, answer for part 1. This is part 2. Part 3 of the problem, I just need to obtain the total emissive flux, which is just the integration of E lambda over all the wavelengths. Okay? So part 3, capital E is integral E lambda over all the wavelengths, and so pi times integral of this quantity 0 to infinity I lambda E lambda T d lambda so harking back, this is the spectral emissive flux about a specific direction. This quantity here. The second quantity is the hemispherical spectral emissive flux. Hemispherical meaning that I am integrating it throughout the hemisphere dimension. 0 to 2 pi and 0 to pi by 2. Then the net emissive flux, or the net emissive power, is essentially taking this hemispherical spectral emissive flux and then integrating it over all the wavelengths. And this integration can be done, but before I do that, we call this quantity as IE, which is the net radiation intensity, okay, or the net intensity. All right, and then eventually the units will be for emissive flux, which is watts per meter square. One can easily prove that. I'm not going to do it. I'm just taking E lambda, which is dependent on micrometers, and then multiplying it by D lambda, which is micrometers, so I'm left with watts per meter square. So let's do it for our problem. Based on the distribution that's given to us. E is pi, which is a constant. It comes out. And you can see that from 0 to 10 micrometers, on the distribution that is given, we have a linear distribution of the intensity, and then it's constant after that. The slope is 10 to the power 3 there. Okay, so I'm just going to have integral from 0 to 10 micrometers. This is the equation of a straight line whose y-intercept is 0, slope times the variable, and then from 10 to 40, these are all micrometers. This is just 10 to the power 4. There. Okay, so this is the slope here. Just want to make a note of it. portion, do the integration, and then you will end up with the answer. So E will be 35 pi times 10 to the power 4 watts per meter square. Check the numbers, but it should be more or less fine. Once again, these numbers are kind of meaningless until we start looking at the ideal surface emission characteristics. That's when we start putting a real spin on these problems. Okay, I'm waiting to get there, but we need to get thorough on these preliminaries. Any questions so far, please? Three things: dq lambda double prime, which we defined. Then I have E lambda. Please remember these terms. There are lots of terms, understandable. And then capital E. Capital E is our good friend, emissive flux. We all know that. This is a new person introduced. It is just the emissive flux per unit wavelength. Okay, and then likewise. Okay, last part of the problem. What we are going to assume for the last part of the problem is that, okay, this area A2 that I have drawn, this is receiving radiation only from the surface A1. It's not receiving radiation from any other surface. This is an assumption that I'm making. Okay, so which means that all the radiant energy that is sent by A1 in the direction of A2 is all that is incident on A2. So in some sense, the amount of energy that is emitted by A1 in the direction of A2 is the irradiation for A2. Irradiation being the amount of incident radiation that you receive, right? The only sticky creature here is that it's not on the hemisphere, it's a surface sticking vertically up, and we will alleviate that in a minute. But before that, I want to write down the following equation. So dq 1, 2, this is the net radiant rate of heat transfer received by surface 2 from surface 1 about a specific direction and wavelength. Rate of radiant energy received by 2 from 1 per wavelength d lambda and specified direction. And this is equal to the following, right? This is equal to I lambda. Watch this. I'm going to say this is little I first, okay? Because I am looking at the radiant energy that is received by the surface 2. But in reality, the surface 2 is receiving only energy from surface 1. So I might as well just call it as I lambda comma E, which is the radiant energy emitted by surface 1. Okay? We're going to change that very soon, once we look at irradiation and absorptivity and all that. But for the time being, this is our approximation, lambda comma theta comma phi. All these shenanigans here. Then I have d lambda. Watch out, d omega 1 to 2. This is the solid angle subtended by the surface A2 as seen by the surface A1, or as seen from surface A1. So this is subtended by A2 as seen from A1, and then multiplied by dAn, that is the portion of what a person sitting on A2 is seeing of A1. And this by definition that we've done before is dA times cosine theta, or in our case this is A1 times cosine theta. You can call A1 as dA1 if you want, but just to make it all convenient. So for us here, A1 is the same as dA1. Let's start cracking them up one by one. So d omega 1, 2 is the only sticky creature here, and this is how we take care of it. by definition, the solid angle subtended by a surface which is sitting on the hemisphere above a surface that is emitting radiant energy, it is imperative that the area normal of the receiving surface, by the definition of the solid angle, is aligned with the line of sight from the sending surface or the transmitting surface. Okay, so this is surface A1, this is, let's say, some surface A2 tilde, because it's not really A2, right? Our A2 is sitting straight up. This is of course 90 degrees here. It doesn't look like it, but it is true. And this has to be in the direction of the area normal, and that's how we define the solid angle, right? So if this is the angle theta, and this is d omega, 1, 2, 3. This is the solid angle that we need. And by definition, this d omega is A tilde 2 divided by the square of the distance from A1 to A2. The structure has become damp, you see. So brittle failure is exacerbated by humidity effects. Okay. So the whole idea is of how do I find this A2 tilde? Given A2 is sitting vertically up, all I have to do is the following. Take the area A2, project it on the hemisphere, and I'm good to go. Okay? So if I look at it, this is A2 really. So I take A2 and I project it on the hemisphere by dropping a perpendicular. And this is going to be A2 tilde, perpendicular here, I'm sorry. This is some angle. This is going to be the same angle theta from geometry. And so A2 tilde is essentially A2 times sine of theta. Does this make sense to everybody? I'm not interested in area A2 because by definition of the solid angle, the area normal of the receiving area has to be along the line of sight. Okay, but in this case that is not the case because the area normal for A2 is horizontal. So I have to take A2 and actually project it on the hemisphere that is surrounding this area A1, and in doing so, I'm already given information on this angle theta, and by geometry that is also going to end up being theta. You can figure it out. And so this A2 tilde is going to be A2 times sine theta. And mind you, in this problem, for the last part, we are not doing any integration over theta because I'm looking only at a fraction of the area on the hemisphere. I'm not looking at the total hemispherical emissivity or something of that sort. Okay, so going back to that, we have dq 1, 2 is now. And notice, this is the intensity of radiant energy coming from surface A1, which is a diffuse emitter, so it is independent of the angle anyways. So this is lambda comma E, lambda comma T only, no theta and phi dependence. Then I'm going to have d lambda. Instead of d omega, I'm going to have A2 sine theta divided by R12 square. So this is actually 1, 2. And the last one is A1 times sine cosine theta. Divide through by the area A2, I get the flux. So dq double prime is just dq 1, 2 by A2, which is I lambda comma E, all of these guys, and then d lambda, A1, sine theta, cosine theta. What is this character? This is the flux received by 2, sent by the area 1 for a fraction of the wavelength d lambda. What do we want? We want the total flux received by A2, which means that I have to now integrate this expression throughout the wavelength range from 0 to infinity, and that's the last part here. And so for us, Q double prime 1, 2 is integral over the wavelength, and theta is 60 degrees. Once again, I am not interested in the total emissive flux. I am interested only in the emissive flux that is received by the area A2 in the direction that A2 is sitting with respect to A1, which is 60 degrees. And so Q 1, 2 double prime is integral 0 to infinity lambda comma T d lambda A1 times sine 60 cosine 60. You do the integration only if you are asked to find the total hemispherical flux. Okay, total emissive flux. This quantity was just obtained some time back. This is nothing but IE, if you recall, IE of T, which is nothing but emissive flux divided by the value pi for a diffuse emitter. Okay. Diffuse emitter meaning the emitted radiant intensity is independent of direction. Okay. An ideal diffuse emitter is something where the intensity is the same in all directions. Real diffuse emitters will emit radiant energy at a fraction of an ideal diffuse emitter. Yes?
What happened to the R12 squared?
Good question. Thank you. Alright. Do the substitutions. I'll upload the final numerical answer. I think E was already 35, something like that. Can calculate it. So this is going to be ending up as 35, that is about 4. This one. And then substitute this for area A1, which is 10 to the power minus 4 square, meter square, and sine 60 cosine 60. R12 is 50 centimeters. Okay? So let's move on. Now, yes, question.
So why did we integrate from 0 to infinity if the wavelength was from
Yeah, sure. So what will happen is that this will be defined only for the region from 0 to 40. Everywhere else it will be 0. Yeah. So this is the most generic expression. And then depending on the fraction that we are interested in, we will invest our energy only in that. Which is, I think, how we wrote the previous expression as well. But then the integration was done from 0 to 10 and 10 to 40. Yes? Can you say that? Can you say that again? So you mean to say this is independent of angle?
Yeah, you just use lambda.
Oh yes, yes. You can typically use it as lambda, but then this is integrated over all the lambda, right? So the lambda is removed. The dependency is removed. You keep the dependency on only the quantities which are actually dependent on it. Here I am integrating it over all the lambda, so this is just going to be IE. And that goes to show that, you know, in reality this I lambda comma E should be written as lambda E theta phi and the temperature. So that's like a train load of people sitting there, so you don't want that. And that's why typically the dependency, the functional dependency is written in the brackets. And just to make sure we are talking about a quantity that is dependent on the spectral characteristics, you keep the letter lambda and you keep the letter E because it depends on emissivity. This is emitted radiation, okay, emitted intensity. If it is irradiation, then the E will be switched to little I, which is the incident intensity. And if it is radiosity, it's going to be E plus R, because it's going to be some part emitted plus some part reflected. And if you recall, we defined radiosity some time back. Don't worry about it. We'll come back to it again. Okay. Ideal surface. And this is characterized as a black body in your book, and that's because of the color of the surface, because it absorbs all the radiant energy incident on it. Not literally the color, right? So we're going to define ideal surface as having the following characteristics. So any surface, or an ideal surface, is a perfect absorber of all radiation incident on it. That's the first thing. The second thing is an ideal surface is a diffuse emitter. Perfectly diffuse emitter. So that the intensity of emitted radiation is independent of the angle, and it is actually the same in all directions. Okay, that's important to characterize. And so here I'm going to say that the intensity that is emitted is I lambda comma b, the subscript b indicating that this is an ideal surface or an ideal body. This is going to be a function of only the wavelength and the temperature. And this is the intensity of emitted or intensity of radiation. We will use the same for emission and absorption as well, so I will not characterize it that way. Two more points to add. Third point. No surface can emit radiation at a greater value of intensity than an ideal surface. No surface emits radiation of intensity greater than I lambda comma b. And the last point is an ideal surface emits radiation in accordance with Planck's distribution of radiant intensity. So I lambda comma b follows Planck's, Max Planck, the German physicist, quite notorious chauvinist, but seminal contributions as well. So, what do you know? It follows Planck's distribution. And we're going to make use of the Planck's distribution. I'm not going to prove it, but if you take any course on quantum mechanics, this is one of the foundational things that they typically talk about. Okay, and this distribution, just a backstory. There are two important events that kind of characterize the Planck's distribution, or which preceded Planck's distribution. They're called the photoelectric effect, and then the ultraviolet catastrophe. I'll very briefly write some notes on it and post it on Carmen. If you're interested, you can take a look at it. Okay? They changed the field of radiation heat transfer, or heat transfer in general. And the problem was motivated by the amount of radiant energy that burning of coal gave out. because coal was the fuel used for engines. So it was imperative that they understand how to characterize the amount of energy that's coming in or going out. And so are emitted. And before Planck, there was Rayleigh and James Jeans, Rayleigh Jeans. They were the ones who came up with a formula that says, okay, this is the intensity of radiant energy emitted by an ideal surface, but it did not follow the actual experimental distribution. And Planck came and then tweaked it a little bit, and then presto, you got that. It followed the experimental results perfectly. I don't know what Planck did, but something special. So here is Planck's distribution. So I lambda comma b follows the following law, okay, or distribution. 2 h c naught square lambda to the power 5 exponent of h c naught lambda kb capital T minus 1. And I'll explain these terms one by one. Okay? H is Planck's constant, and this is units of watts per meter, micrometer, steradian. So this is your typical I lambda comma E, but for an ideal surface. So if I have an ideal surface, if I want to calculate my I lambda comma E, just calculate it using this formula. If I'm given a wavelength, if I'm given a temperature, just plug and check based on Max Planck's distribution. If I want it for a real surface, what do? I say that, okay, hey, I do have it for an ideal surface. The real surface is going to be at a fraction of what the ideal surface does. That fraction can be obtained from experiments. And so I multiply this value by that particular fraction, which is called as your emissivity. And I get I lambda comma E for a real surface. Once I have I lambda comma E, as you see in our problems, you can calculate the emissive power or the emissive flux. So calculate the emissive flux, do the same thing for irradiation. I get Q net radiation, or the net radiation flux, which is all that we are caring about. Right? So here H is Planck's constant. I have the value, and for the life of me I can't remember that. This is 6.626 times 10 to the power minus 34 kg meter square seconds. C naught is the speed of light in vacuum. Which is in vacuum is 3 times 10 to the power 8 meters per second. And K suffix B is the Boltzmann constant. And Dr. Ludwig Boltzmann. The Boltzmann constant has the following value. It's 1.381 times 10 to the power minus 23 kg meter square by second square Kelvin. And it should make sense that the quantity defined here will be dimensionless, obviously. Okay, you can check it and see, and we're not going to do that. So this is for an ideal surface, and I want to draw this. There are two ways of drawing this, one on a log plot, and then one on a linear scale. We try to draw both. But before doing that, here's what I'm going to do. You may recall from our problem that we solved, the hemispherical spectral emissive flux. Okay, if you recall, this was the following. E lambda is this is the one that we had, right? And here I lambda comma E is the intensity of radiation. But if I do this for a real, for an ideal surface, then what happens is that my ideal surface is a diffuse emitter, which means that I can take this guy out of the integral, and I'm just going to have integral sine theta cos theta d theta d phi, which is equal to pi. So for an ideal surface, E lambda comma B, which is a function of only lambda and temperature, okay? The suffix B represents the fact that this is for an ideal surface or an ideal body. This is going to end up as pi times I lambda comma B of lambda comma T. And this is called as the hemispherical spectral emissive flux for an ideal surface. Now the nice thing is this. I take this creature, E lambda comma B, and integrate it all over the wavelength lambda. You know what happens? I end up getting the Stefan-Boltzmann law, which you may recall is sigma T to the power 4. Okay, and the details are left to you. We're not going to do the integration. It is just that taking this big guy here, performing the integration over lambda. There will be a change of variables and so on, because there's an e to the power lambda, there's a lambda to the power 5, and eventually everything will work out, and this is a Stefan-Boltzmann law. And it is not that Stefan and Boltzmann took Max Planck's distribution, integrated, and said that okay, this is the law. There was a lot of other details that went through coming up with this, especially the experimentation involved in proving that this was indeed the emissive power of a real surface, of an ideal surface. Okay, all spectroscopic measurements. And spectroscopy, the field of spectroscopy where you look at the visible spectrum in order to glean an idea of the intensity of the radiation or the energy, it was not as well developed then as it is now. Photospectrometers and so on were difficult things at that point in time. 1906, 1910, 1912. World War I was happening or beginning to happen at that time. So the world was shaped by a lot of events out of the control of scientists. But science still continued to pursue good things. So that's one. Now I'm going to draw this E lambda as a function of lambda. This is lambda in micrometers, and this is E lambda, lambda comma T, sorry, this E lambda comma B, lambda comma T, units. There will be no steradians here, it will just be watts per meter square micrometers, okay? Because you're multiplying by the angle phi, which is in steradians. And this is going to be a function of temperature, so for different temperatures I'm going to get different curves. This is going to be a log-log plot, log-log scale. And here is the distribution. And so on. So these are all curves for increasing temperature. Okay, so as I increase the temperature, I get these particular curves. So first one typically is like 100 Kelvin. And this is close to 5000 Kelvin. The outer surface temperature of the sun is around 5,700, 5,800 Kelvin, and the spectral intensity that is obtained from the radiation emitting from the sun is closely approximated by a curve which is between 5,000 and 6,000 Kelvin, which is why the sun is modeled as an ideal surface, because the spectral intensity of radiation emitted by the sun follows in some sense the distribution that is drawn here. Okay, but portions of the radiation are absorbed as the sun sends radiant energy onto the earth. Ozone absorbs some, oxygen molecules and hydrogen molecules absorb some. So there will be pockets where they will not necessarily align perfectly with the real surface distribution, but more or less it's good. Notice a couple of things. The peak these peak points, you see, are going to keep shifting on to the left as the temperature increases. Okay, so two things that I want to make a note of here before I leave you all for the day. First thing, for a given wavelength, can everybody still see my writing clearly after I erase the board multiple times? It's like ghost letters sometimes pop out. But let me know if you cannot see it clearly. So for given lambda, E lambda comma B, it increases with temperature. Right? It is quite evident from the plot. Second thing, the maximum of E lambda comma B for the max value of E lambda comma B, that is the maximum value, occurs at some wavelength lambda called as lambda max, which keeps shifting further and further to the left as I keep increasing the temperature. Okay, so this is getting displaced to the left, whose value keeps shifting to the left. And how do you find the peak? You just differentiate with respect to lambda, and you obtain the following, very last sentence for the day. To obtain lambda is equal to lambda max, for which E lambda comma B is a maximum, you differentiate the E lambda comma B with respect to lambda and set it equal to 0, and if you do the differentiation, you end up with the following equation: lambda max times T is 2898 micrometer Kelvin, and this is called as Wien's law of displacement. And once again, it is not that Wien, the scientist, decided to take Max Planck's distribution and then start differentiating it and then obtain an equation and call it after himself. Okay, there are many things that went in behind how these calculations, specifically experimentation. And with that, I'll stop and we'll come back and start looking at more of these things.